just okay. Now it's recording. So Manuel, thank you very much.
Denis, você consegue ver o meu ponteiro, Denis? Só para confirmar.
Yes. Sim,
ok.
E aí, Manuel, você vai fazer um intervalo? Se você for fazer, eu paro a gravação no meio, aí ficam 2 para não ficar um vídeo muito longo, tá bom?
Tudo bem, Denis, ok. A minha ideia seria fazer talvez 5 minutos, não sei.
Pode ser, mas eu só paro esses 5 e volto, daí... Mas beleza, eu vou seguindo aqui. Um abraço aí para vocês. Obrigado, Manuel.
Obrigado. Okay, guys, so good morning for all. So if you have any question, I could try to respond in Portuguese or try to repeat something in English, okay? Because it's not trivial for me to present in English. So the subject of this presentation is about characterization of petroleum reservoirs. So it is important in this class because we need this kind of characterization to input our data in numerical simulation of reservoirs. So in this presentation, I'm going to talk about the construction of geological models under uncertainties. So I'm going to show how to construct a lot of equiprobable models to use as input in numerical simulation, because in numerical simulation, most of all steps in numerical simulation, we need a lot of image because we have a lot of uncertainty underground. So the risk analysis step, we need a lot of image. The choice of a strategy, production strategy, we need a lot of models, and also history matching. So the object of study in this presentation is what we see in this slide. So we needed to define the porosity and permeability, and that is characteristic from the reservoir to use as input in reservoir simulation. From this point until we input this data in flow simulation, we go through several steps that I'm going to talk about it. So this is the topics. So to construct a model and to carry this model into flow simulation. So data acquisition, geological modeling, upscaling. So the upscaling is we need to transfer the data from geological model to flow simulation. So we need to make upscaling our data because we cannot use geological models in reservoir simulation due to the limitations in flow simulators, but also due to the higher computational time to simulate models with high resolution. So we need to make an upscaling. Then I'm going to talk about flow simulation and uncertainty modeling. So, as you know, most of our projects that we have now in Unisim are related to carbonates, which are more challenged than siliciclastic rocks. So here in this table, we have a lot of characteristics that differentiate carbonates from siliciclastics. So, as we know, carbonates are more prone to diagenetic process. So there is a high probability to occur secondary porosity in this kind of carbonates. So in this case, we have more challenge in carbonates than in siliciclastic rocks, mostly because carbonates are more heterogeneous and so are more difficult to characterize in geological modeling steps, but also there are more challenge in the upscaling process that I'm going to show. And also in flow simulation, it's quite difficult to characterize this type of reservoirs because we cannot use only single porosity flow models that I'm going to show, but we need to test also other flow models like dual porosity flow models where we have a fracture system and a matrix system. So the challenge that I was talking about are mostly because 60% of our worldwide reserves are in carbonate reservoirs. So they have a complex porous system because we have heterogeneity in several scales. It is quite normal in carbonate reservoirs that we need to construct a diagenetic model that characterizes, that show all process in the depositional model in this type of reservoirs. It is quite important because it shows how these reservoirs has been changed all over the time. It is normal in these reservoirs the presence of fractures. Also, it is normal to the importance to study outcrops that are analogs from the field that we are going to study. The seismic resolution is another important input data in carbonate reservoirs. However, carbonate reservoirs can have fractures which are not easy to characterize by seismic due to the small resolution from seismic. Also, we normally in carbonate reservoirs we have very thin layers that we don't have in silicic classic reservoirs. So these thin layers are also not visible in seismic resolution. So we have here a lot of challenge in the seismic in order to try to improve these attributes from seismic, like amplitude, in order to try to improve the characterization of carbonate reservoirs. Fluid injection in carbonate reservoir is normal to inject another type of fluids different from water, like gas, water alternated with gas, that in other posterior class people will talk about it. Then in this class we're going to talk about this type of other type of injectant fluids. And numerical flow models, as I talked about, normally in flow simulation, mainly in sandstone or silicic class reservoirs, the people use a single porosity flow model. So we have only a grid. So in carbonate reservoirs, it's normal to use other type of numerical flow models, like dual porosity flow models, where we have a fracture system and a matrix system. And there is a transfer term between the matrix and fracture system that controls the fluid exchange between both grids. So a big question is how to combine the data from different scales, because we have the micro scale, we have the micro scale that comes from laboratory, the macro scale that comes from well cores, the mega scale that comes from well logs, and giga scale that comes from seismic resolution. So one of the challenges, and this challenge is a common challenge not only for carbonates but also for silicic clays, is how to combine all this data that comes from different kind of samples. So the first step in a geological model is the data acquisition. So we needed to study diagenetic models, like in this figure. In this figure, we need to combine these diagenetic models also with well log data, with plugs. In the carbonate reservoirs, we have the fracture system, so we have another kind of data that we need to characterize, and try to combine all these with a seismic data. Okay. So as I talked about, we have well logs, core data, seismic, structural data, positional model, diagenetic model. So this is the normal input data that we use for geological models. Here we have an example. So in a well log data, we can see that we have the I'm going to show here just for examples here that the gamma ray log. So higher gamma ray normally is related to a higher content of organic matter. Okay, so like in this case, higher gamma ray is related to shale, so a non-reservoir layer, and the smallest gamma ray normally is related to a good reservoir property. Here is another common log that we use for porosity, that is density log. Resistivity log, which is also very important because it determines the ability of rocks to conduct the electrical current. So it's used to determine the differentiate the carbonates from water zones, and also indicates the permeable zone. Okay, so here we have the sonic log that is also common. It emits a sound wave and measures the travel time. With this time, it is possible to calculate the porosity. So this is only 4 examples. But there are a lot of other logs. Like in carbonate, they use a lot the magnetic resonance that is very good for calculate porosity and permeability, because this kind of log can differentiate the good porosity within the bad porosity. So another input data is the seismic. Okay, so the seismic is, we have here a small figure explaining how does this works. Okay, so the boat emits a wave, and the time delay between transmission of sound waves and return gives an idea about the physical properties or the type of fluids in the rocks. So the different density in the rocks and the different type of fluids, this makes has an influence in this time between the transmission of the sound waves and return. So it gives an idea about the type of rock and the type of fluid that we have underground. So step 2 is the geological model. So, okay, this is an image from the petrel. You can see that this image is from Petrel. It is a software that we use for construct geomodels. Okay, so you can see that this is in a orientation that is related to all steps that we need to construct a model. So make horizons, make the grid, scale up well logs that I'm going to talk about, the Facies modeling, the Petrophysical modeling, then we have the upscaling. So Petrel is very intuitive for people that construct geomodels. Okay, so maybe some of you guys will gonna work in Petrel. So the first step in geological modeling is stratigraphic modeling. So the stratigraphic modeling consists in defined stratigraphic units. So such units can be distinguished on the basis of their lithology, their fossil content, or the positional chronology. So this is an important step to define horizons. As you can see here, we have 3 horizons. So you can see that the people that have defined these horizons define in a way that this kind of zone is different by some reason from this zone and the other zone. I'm going to give an example. So imagine that this zone here has fractures and this zone does not have fractures. So it is very important to create a zone here, because in the forward step, in the end of the construction of the geological model, if you want to input fractures in this zone, you need to create this zone before. That is in this step. So if you forgot to define this zone as example, you need to return back and define the zone, because you cannot, if you don't have this zone differentiated between this one, it is difficult to input fractures only on this zone. Okay, so this is only an example, but there are, as I write it here, it is based on lithology, not only fracture content, fossil content, the positional chronology. So there are a lot of geological trends that differentiate the zones. So another step is the structural model. So another attribute that helps in structural modeling is the seismic. Okay, it is very important, seismic, to define horizons. These horizons that I present here before. So seismic gives a good hand in this one. So Another step is the fault modeling. Okay, so also the seismic is very important to the fault modeling. When you talk about faults, it's different from fractures, because fault is normally associated, is always associated with a kind of movement between the stratigraphic zones, between layers, and normally is related to several kilometers. And when we talk about fractures, we talk about features that have like 100 meters or few meters, so it's a different scale. Fault is related to tectonic movements, and in that is a higher scale than fractures, okay? Then normally the fractures are a result from a fault movement. So now I'm going to show here, so we talk about faults and horizons modeling. So here we have a figure, so this is where we are now. So we have characterized the faults and characterized the horizons, okay? So the current stage, now we have the faults, we have the several horizons, in this case 2 horizons in this example. So now I'm going to talk about the upscaling, well-log upscaling to structural grid. As we see here in this left side, you can see that this is a well-log data. So this is in a one-dimensional property. So the well-log data comes from 20 centimeters by 20 centimeters. So for each 20 centimeters, we have a data of porosity, of permeability, and normally is 20 centimeters. But the question is that we have a structural grid, and we need to make upscaling. So this is the first upscale that we need to make. That is related to well-log upscaling to the structural grid. Because in the structural grid, we have a 3D block, not a 2D or 1D block, okay? So we need to make an upscaling. So this is the first upscaling. And also, it's not only because we have here a 3D block, but also because normally this block in our geological grid is in a smaller resolution than well-log, okay? So normally in the geological grid is higher than 20 centimeters or grid or block. So now we have made the well-log upscaling, and the next step is property modeling. Okay, so the property modeling consists in to make the spatial variability all over the model. Okay, so we have logs, we have seismic, and we need to calculate what is the porosity and permeability that is in the middle of the well logs of these wells. So here we have example 4 wells. This one is here, this one is here. So we need to populate the permeability. And next, I'm going to show forward in this presentation the upscaling process that we're going to input in full simulation. So the first step in property modeling is the facies modeling. Facies modeling is important because the porosity, permeability, net to gross is normally attached to the facies modeling. So normally these properties, porosity, permeability, net to gross, is always dependent from facies modeling, okay? So facies modeling is not, it is common, but it's not always, it's not always necessary to make the facies modeling, but normally it is an important procedure, okay? So for the facies modeling, we have 2 kinds of processes, stochastic and deterministic. The stochastic generates equiprobable models, okay? So imagine that we have 2 or 3 wells in our reservoir. So we don't know what is in the middle of these wells, okay? So we never know what is in the middle. So one of geostatistical techniques is to generate equiprobable models. So generate models that has uncertainty between wells. That's the name, that's why it calls stochastic. In this kind of stochastic, we have different techniques. Objects modeling, so it's useful. The objects modeling, as the name is called, it generates objects. But it's a kind of specific objects, like if you want to model channels, you use objects model. This is useful not only for silicic lasts, but also for carbonates. But the common technique, but one thing I forgot, is that normally objects modeling is a kind of secondary type of modeling. It's not a unique modeling technique, because normally we apply a Gaussian sequential simulation, and then if we want to model some kind of specific features, then you apply the objects modeling, okay? So we never apply only objects modeling for model a reservoir. Normally, it's a consequence for a Gaussian sequential modeling. That is quite normal. This is the Gaussian sequential simulation is the most common technique for all reservoirs. I'm calling here that is common in silicic class, but also some kind of carbonates we apply this technique. And we have another one that is the truncated Gaussian simulation, that it's very useful because you can integrate typical depositional environments for carbonates. So you can simulate transgressions, regressions, movements of shoreline that is related to a short and long term of relative sea level change. And this kind of environments in the carbonates, if you use the Gaussian sequential simulation, it's not possible to simulate. And this kind of environments is normal in the carbonates, because normally they are depositional in the kind of marine depositional environments, okay? And we have, in stochastic, you have also other techniques there, but they are not so trivial, okay? Like you have a multi-point statistics model. So if some of you guys will gonna work in Petrel, you're gonna see like that kind of I think it calls multiple statistic points. It's a kind of technique that you can enter an image of your reservoir, like a paint. You can draw something and you can input that kind of paint in a Petrel, and then you can try to make stochastic modeling that is close to that draw that you have done. So it's another kind of technique that is also used in carbonates, but it's not so trivial. So I'm not gonna show here, but it's not, because it's not so trivial. It's a new technique all over, like the last 5 years, 10 years maybe. So yet another technique is the kriging. So this is a hold technique, kriging. However, and this is a deterministic technique, because it always gives the same model, the kriging. So there is no uncertainties in this kind of technique. So it does not give a kind of variability. I'm going to show in next slide. So this kind of technique is less useful for field development, because as I talked about in the first slide, all steps in a reservoir simulation, we need a lot of equiprobable models, okay? So we need to work with uncertainty. So we need to work with models that are realistic, but also considering uncertainty. So here I'm going to show the difference between the stochastic models and the kriging models. So on left side, you can see a stochastic model. So you can see that you have an image without defining transitions, which is very close to geology. So what we see in geology, we normally don't have a very defined transition in geology. You can see on the right side that the kriging, it is a very smoothed image. We cannot see uncertainty in this kind of image. We have a well-defined transition. So it is not very useful in a reservoir simulation to work with uncertainties. Here you can see another comparison. You can see in the first image this kriging here. So we have here well locations. Okay. Here we have a kriging porosity. Here we have a simulated porosity. So for one realization, and here we have another stochastic porosity for another realization. So you can see that first in a kriging porosity is very smooth in the image, okay? But you can see that here in stochastic image that is you have a more variability in our data. Which is better. So you also can see that we have a higher variability away from the wells. So it is very useful, this kind of image in reservoir simulation, because you never have the same response. Okay. So this is another comparison between kriging porosity. This example is for porosity, but the kriging exists for porosity, for facies, for permeability, for net gross, for all kind of property modeling that you're gonna which is necessary. Okay. So after we make the facies modeling, we have another step that is related to petrophysical modeling. So again, we have the stochastic modeling and the deterministic modeling. The stochastic, we have two techniques, the Gaussian sequential simulation and the Gaussian random simulation. They are quite the same, okay? The only thing is that the second one is proper when you use a secondary variable like permeability, like you model porosity, like if you model permeability, normally we enter the porosity as secondary property, because normally they are both a function of each other, okay? So normally the Gaussian random simulation is proper for use this kind of secondary variables. However, normally they give quite the same result, okay? And again, we have the deterministic, the kriging option. So here I'm going to show an example about the sequential Gaussian simulation. How does it works? So here we have wells, okay? Like in these points where we have here stars, it's a kind of points that we have. It's the points where we have wells, okay? So the first thing that is important is that for each, why this is called Gaussian simulation. So any kind of simulations that you use not only for facies but for all properties, normally they are also always related to a Gaussian simulation. Why? Because each of these blocks from the grid that you have in geological model has a Gaussian probability for occur at a type of value. Okay, so you don't see this Gaussian distribution, but each block has this Gaussian distribution internally in the software. So anytime that you make a simulation, so a stochastic simulation, you have a different value from this Gaussian simulation, Gaussian distribution, okay? That's the reason that is never the same value, okay? For each realization that you do. It's never the same value because you have a Gaussian distribution for each block. You don't see that, but you have this Gaussian distribution. So, and how the name sequential, it comes because for each block where the permeability or porosity is calculated, the simulated data uses the previous calculated data. So it uses the well data, but it also uses the previous calculated data. That's why the term sequential, okay? So the Gaussian simulation is related that we have for each block a Gaussian probability, a Gaussian distribution that represents the probability of occur that kind of value inside that distribution. And sequential is because it is calculated sequentially, okay? So, but how is defined this Gaussian? This Gaussian distribution for each block comes from the input data that we insert in our geological modeling. So the seismic, the well data, the variability that is related to variogram that we're gonna indicate in our geological modeling, the spatial continuity, it is also related to variogram, and spatial correlation, porous permeability, and other kind of data. So this is an important step that you need to know about Gaussian simulation. So now I'm going to focus on carbonates, which is has some kind of difference between conventional models, because we needed to integrate other kind of techniques, okay? And we need to integrate other kind of techniques that are, because we have heterogeneities in the several scales. So in a reservoir, carbonate reservoir, you can have a vagular porosity, we can have fractures, we can have moldic porosity. So it's quite difficult to integrate all this data in carbonates. So, and it is quite different from silicic cluster reservoirs. That's why we need to study other kind of techniques different from a Gaussian simulation. So one of the different techniques that we use in carbonate reservoirs is discrete fracture networks. This is used over the last 30 years, and as I told before, in carbonates we normally have the presence of fractures in the whole kind of scales. Okay, we can have small fractures, we can have medium fractures that are close to 500 meters or 100 meters, or we can have large scale fractures that are higher than the resolution from the seismic, okay? So this discrete objects modeling is exactly as you see in this image on the right side. So these are the discrete objects that represent fractures. Normally, this kind of technique that you have in Petrel and other softwares is used for fractures, but also you can use that for like to karst modelings, okay? So like an example, we have a project in Unisim that people are trying to also model karsts using this kind of technique, okay? So when you use the discrete objects modeling, you have several inputs in this to make a discrete objects modeling. Intensity fracture modeling, you need that. It is the intensity of the fractures that you see in the cores, normally in the cores, because it's the plugs is the only way, one of the, I think the main way that you can calculate intensity of fracture models. So you have a lot of uncertainty in this kind of data. The length of fracture, dimension of the fractures, the depth and the orientation and aperture of fracture. These are the input attributes that you use for construct the discrete objects modeling. Oh, sorry that this slide is in Portuguese, okay, but I forgot to translate this one. So here you see an example about the discrete objects modeling applied to a very heterogeneous scenario. You can see here that you have, so this is 100 meters, this block, this is 500 meters. So we have here a zone that is like an interwell region, okay? So then we see here, so you have here fractures, large-scale fractures that are close to 100 meters. Then we make a zoom here, and you can see that we have a small fractures here in green one. Then you can model like something like vugs here that you see in red. So you can model a lot of things in carbonates that are not trivial in silicic-class reservoirs, okay? So all these kind of vugs, fractures is quite normal in carbonates. You can use these discrete object models to simulate all this kind of data. Then I'm going to talk later is how do you convert this data as an input property to use in flow simulation, okay? This is done, we done this using the upscaling, okay? So in fracture reservoirs, we have 4 kinds of fracture reservoirs. The type 1 provides the essential porosity and permeability to the reservoir. So the second one provides the essential permeability, ons. The fractures provide the essential permeability. The type 3 provides a permeability in already producible reservoir. And the type 4 is, it does not have a positive impact on the fractures, but can create strong anisotropies. So the normal one is the type 2, which is the most common fracture reservoir, okay? So you have a kind of, the type 2 is a kind of reservoir that where you have the porosity is in the matrix. So the porosity is in the matrix, not in the fractures. But the fractures are provide the essential permeability, are the main conduct in the reservoir, okay? This is the most common reservoir is the type 2. The type 3, it is common in some kind of pressal reservoir. So you have an already producible reservoir, so the matrix is permeable and there's a higher porosity, and you also have fractures that assist this permeability, okay? So the type 3, type 2, type 3, the type 2 is the most common, but the type 3 is also useful to occur, okay? The type 1 normally is like, so the fractures are porosity and permeability also comes from fractures, okay? So in this kind of type 1 of reservoirs, normally we don't have high recovery in our reservoirs because fractures, as you know, don't have a lot of porosity, don't have a lot of capacity to have a used reserve of oil, okay? Now I'm going to talk about the control parameters. The control parameters are the geological trends that can be used for control the fracture distribution. So these parameters are parameters that we can use to populate or discrete objects or fractures in our modeling, okay? So I'm going to show why. So this is an example. Grain size are important in fracture as a relation to fracture distribution and intensity, porosity, matrix porosity as also is also related to fracture distribution, intensity, layer thickness, and structural position. So here you see an example, okay? So for a matrix where we have a fine grain, you have a huge fracture intensity. So normally when we have like a matrix with the coarser grain, so larger porosity, you can see that we have a small fracture intensity. So here you can see that also the porosity, the fracture intensity is higher when we have a higher porosities in this case, okay? So here also you can see the relation between the thickness of the layer with average fracture spacing. You can see that when our layer is very thick, so the fracture is very spaced. So the intensity of these fractures is smaller, okay? Smaller intensity of fractures results in a higher fracture spacing, okay? Another control parameter that I talked previously is structural position, because normally near falls we have more fractures. So this kind of trend that I'm showing here, the grain size, the porosity from the matrix, the thickness of the layer, as I talked previously, normally we don't have a lot of data in fracture reservoirs. We have well logs, but well logs are not so good for fracture reservoirs. You can use plugs to define where you have fractures or not. Seismic is not so useful to define where are fractures. You have well tests, okay, that gives an idea about the permeability of these fractures, but you don't have a lot of data to characterize this kind of data. So these kind of control parameters are useful to use as input to distribute these fractures, because this is this kind of input parameters. You have a lot of bibliographic data that shows that these kind of input attributes are very useful for distribute and very useful for correlate the fracture distribution. So until now we have talked about static property modeling, structural modeling, falls, horizons, swell log upscaling, facies modeling, petrophysical modeling. We talk about also the objects modeling, fractures, vugs. You can use the objects modeling for fractures, vugs, caves. We talk about input attributes for the objects modeling, that are the aperture of fractures, dimension of the fractures, the intensity of fractures, and we also talked about the control variables that you can use to distribute these fractures, okay? So now I'm going to talk about upscaling. So all these steps that I talked about are related to geological grid, okay? So are related to a high resolution grid. So with small blocks that useful to try to capture all kind of heterogeneities in reservoir. However, this kind of grid, very refined grid, is not useful. It's not useful. It's not possible to use that in reservoir simulation, because we have simulator limitations, and we need faster models, because as I'm talking about, we never work only with a single model. We work with equiprobable models. So we work with 100, 200 images. So we need models that are very fast to simulate, okay? Here we have the two. We need to reduce computational time, but we also have the simulator limitation. So this is important because, as I talked about, history matching, for the history matching that the forward class someone will gonna talk about. Uncertainty analysis and risk, we also need a higher number of simulations, and production strategy optimization, we also need a higher number of simulations. So the upscaling techniques, we have, this is a resume that we have possibilities that we have in conventional softwares, okay? We have different upscaling techniques, but normally is in non-commercial softwares, okay? So this is the common techniques that apply. For porosity, normally porosity is always the arithmetic average. And net gross and saturation, normally saturation, I write here saturation, but normally saturation we define in flow simulator, not in Petal, okay? So the most important is porosity and net gross, that normally for upscaling we apply the arithmetic average. Permeability, it's a kind of difficult property, because you can apply in geometric and harmonic average. You need to compare which one is better. Also, the rational average that is a mix of geometric and harmonic and arithmetic average. It's also plausible to apply. However, permeability, normally it is common that people compares all kind of possibilities, okay? Normally in siliciclastic, geometric or harmonic average is enough to have a good upscaling result. But normally in carbonates, it is important to apply numerical methods. So these numerical methods for upscaling techniques, they make like internal flow simulation. You don't see, but the upscaling is based on an internal flow simulation, numerical. That's why the name is numerical methods. Or also you can see in books flow-based methods, okay? So this is very useful for carbonates because carbonates normally, they have thin layers and they can have huge transitions with from non-reservoir layers for higher for layers with higher permeability. That's why the reason that normally numerical methods are very useful for carbonates, okay? However, these methods are not so fast as analytical methods like geometric and harmonic. So normally it results in a higher computational time. In carbonates reservoirs, so normally in carbonates reservoirs, we separate the upscaling, okay? So we separate normally in heterogeneities that are close to simulation grid block. I can translate this and say that this is related to fractures. So normally in carbonate reservoirs, we separate the fracture upscalings that is defined that we always model with that kind of technique that I talked previously, that is the discrete object model. And then we make upscaling for the matrix. Matrix, heterogeneity is smaller than simulation grade block. That are matrix or very small fractures. When we have small fractures, it is not necessary to model as a discrete objects. There are techniques that you can model small fractures implicitly in a matrix, though, so they're gonna be inside the matrix, okay? So in carbonate reservoirs, normally we separate this one. In the upscaling procedure, you can try to simulate a reference model, okay? So you can, this reference model is useful for validate or upscaling. So we're not gonna have a reference for 100 or 200 models. Only one reference. You can try two. Is very useful to make an upscaling match procedure to see if the upscaling that we have chosen previously is correct or not, okay? Then you can put 2 L's or 3 in this kind of reference and compare with the coarse grid, okay? Then you can see if the techniques that we have chosen, it is useful or not. It is not normally in industry, they don't have a reference model. So normally they use histograms or just histogram is very useful, okay, to see if the permeability or porosity distribution in the coarse grid is quite similar to the refining grid is useful, but in our case, we think, and we have studied this in Unisyn, that is not enough to say that our dynamic behavior is quite similar to the geological model, okay? So it is very important to make an upscaling matching procedure after we make an upscaling to guarantee that our simulation model has a similar response to the reality that we call the geological modeling, okay? Then in simulation model, I'm going to talk about it. You can use a dual porosity model, dual permeability, or a single porosity model, and you can test different flow models and compare to this reference and see which is the best one. The next one, so one important thing is that I have talked about the discrete object modeling, okay? So the upscaling these fracture networks that comes from the objects modeling, it's quite different than the conventional upscaling. So in this case, you have discrete objects that are the fractures that are similar to objects. So you don't have a grid here. You don't have a grid block here. And to use this data in flow simulation, you need to calculate how is the influence of these objects in an equivalent block property model, because in flow simulation you cannot enter this kind of discrete objects. You need to enter this kind of data as a block property modeling. So the upscaling fracture networks is quite different from the conventional upscaling procedures where you have the porosity, permeability defined in a grid block, in a geological grid. So in this case, you don't have, you have only objects, and you need to make an upscaling procedure to an equivalent block property model. So the output data after this upscaling is that you're going to have effective permeability, you're going to have a fracture spacing, and a factor porosity. So when you do these upscaling fracture networks, you have these properties, but you also have the other properties that are related to matrix porosity, matrix permeability, net gross. So you have a lot of inputs, okay? So in flow simulation. So the upscaling methods for the fracture network, you have two kinds of methods. You have the analytical method, that is the Hoda method. So this method is an analytical method, so it's defined by statistical calculations, and you have numerical methods that in bibliography you can call it as a block K. So these kind of numerical methods in fracture networks is defined through an internal flow simulation. So as I showed in a matrix that we talked about a numerical method, here for upscaling methods for fracture network, you also have a numerical method, okay? Which, as in a matrix, requires a huge simulation time. Huge simulation time to make this, huge computational time to make this upscaling method. However, I'm going to show here an example about the numerical method for the upscaling fractures and the analytical method. Here we have a block. So this is the block where you're going to do the upscaling of these discrete fracture networks. This is only an example that I'm going to show. So the upscaling of discrete fracture networks consists in convert these discrete objects into a block property. So when in this example, you can see that you have disconnected fractures. So it is quite plausible to say that when we make the upscaling of these fracture networks, you don't gonna have a permeability in this block because they are not connected, the fractures. So if you have flow that is coming from here, it is not expected that this flow will gonna pass through this block. So, but the problem is that when you apply the analytical method, that is the Hoda method, it gives a huge permeability. Because why? Because this analytical method, it makes an arithmetic average between the permeabilities from these fractures that are inside the block. So it does not consider the connectivity. And in numerical method, it shows a real value that is 0. But the problem is that it is quite difficult to use this numerical method, okay? Due to computational time. So normally we can apply this numerical method only in a small portions of reservoir. Then you can use that small portion to calibrate the full model. Okay, you can use that response that you have in a small portion of reservoir and try to extrapolate that response in all reservoir. So now we have the final situation here. That is, we have the net gross model, we have the porosity model, permeability, the fracture spacing, the fracture permeability. So we have construction model, we have done the upscaling model, and next I'm going to talk about the flow simulation. So I think now we can make a small break here before start the full simulation, and I think that we can come back in the next 10 minutes. Okay, it's okay for you?